If you remember from the first part of it, before we even started the class, we started kind of a little earlier than Dodge City. I had some review problems on logs, and this is our log chapter. And before we start logs, we really need to kind of go over what exponential functions are, because logs and exponential functions are connected because they're inverses of each other. And an exponential function, remember, a function is going to be, okay, let me just go ahead and draw. A function will always be a member where the member of the domain has a unique member of the range. So in other words, that's why that vertical line test, remember, if I had weird graph like this, okay, where we had like from last chapter, this is still considered a function, even though it doesn't pass the horizontal line test, because it's not one-to-one. It would be a function because of the fact that the vertical line test passed. And the vertical line test just means that I would not have any values here that would overlap. So in other words, like that would obviously give me a false reading for the vertical line test, because there would be three values of y connected to this one value of x. But today we're still going to be working with functions, so all of these are going to be functions. But they talk about the exponential function, and honestly, there's probably a lot of this is a chapter where there's a lot of application. So if you ever go, where am I ever going to use this in real life? This is the chapter that I can answer questions quite a few places. We'll see this exponential function when you talk about like growth and decay. You talk about like population growth, it's exponential. If you talk about like a drug, let's say a drug has a half-life of something, it's in your body for a half-life, then that's a decay. That's going to be, but it's still considered an exponential increase or decrease. So let's go ahead and just jump into like the first one. We have an example where we have f of x is going to be 5 to the x power. So again, my exponential value is going to be the variable. And so when I put it back into here, I'm going to start off with x equals 0. Then that means my y is going to be 5 to the 0 power. But anything to the 0 power is what? 1. Very good. And some people, I do think that I'm going to show you, I've seen this a lot, that's the case, and that is not the case. And part of the reason is that I'm going to show you is that we're going to look at the values like of -1 and 1, and you're going to see that it's going to get close to this value where y or x is equal to 0, but it's never going to actually hit it. So where y is equal to 0, and it's never going to hit it. So it's an asymptote. So if I have the next one, if I have 5 to the first power, that's going to equal 5, and 5 to the second power is going to be 25. And so we jumped up significantly from that. Now if I go back down to the -1, if I have 5 to the -1 power, what did you have to do to make that power, that negative power, 1, to be positive? Yep, you move it down. And so in other words, it's already, if it's on the top part of my fraction or the numerator, that means I have to put it on the bottom number, or bottom. And it's going to be then, if I have nothing on the top left, I don't put 0, I'll put 1 over 5 to the first. I always say on my exponents, if you cross the line, you change the sign. So then if I have then 5 to the -2 power, that's going to be the same as 1 over 5 squared, which is 1 over 25. So then I'm going to go ahead and plot these points. And so I'm always going to have this point right here when on an exponential function, when it's in this form, I'm going to have, no matter what my base is, because has a base of 5. So if I had a base of 100, I'm still going to have, when x is equal to 0, y is going to be 1. But then it changes significantly. When I go when x is equal to 1, I'm up to 5. 1, 2, 3, 4, 5. And so I'm going to plot that point at 1, 5. And then at 2, 25, I'm just going to put it way up here, okay, because I don't have, my graph isn't large enough, but it's increasing significantly. And all of these points, what's happening is it's going down and it's going to connect. But then if I go ahead and go to -1, I'm already at 1/5. So I'm going to come up just a little above my x-axis. When x is equal to 2, negative at 1/25, which is 1/25. And so you can see it's getting really, really close to that asymptote, but it actually never, ever hits. And so these are going to be then the standard graph. And so when I talk about parent graphs or parent functions, this would be like the parent, kind of a parent function. You need to know the way that it kind of lays when you have a standard number to a power, to x is the power. And they're going to refer to what happens when we have the characteristics of the exponential function. In other words, they're going to say if f of x is equal to b to the x, and in this case, b to the x is going to be any base. And so it can be, in our case, the problem we had before was going to be 5, but we could have any number we had. So the domain is going to be this. This is going to be my exponential function for b to the x, and that's when b is going to be greater than 1. But with b is going to be between 0 and 1. In other words, a fraction. Okay, so let me go ahead and give you just an example on what that makes sense. So I'm going to draw an x and y axis again. I didn't need to go that high. But if I have y is equal, now what they're talking about for this function right here is when it's going to be a fraction. Let's say it happened to be 1/2, and then it's going to be then to the x power. So what happens is, when I have x and y, we still have that same function. When x is equal to 0, I have 1/2 to the 0 power. That's still going to be 1. And if I have when x is equal to 1, now I'm going to go ahead and say that I have 1/2 to the first power. Well, now I'm going closer to that 0, so when x is 1, y is getting smaller. If x is -1, what happens is, if I have a -1 to 1/2 to the -1 power. Well, in this case, that I can always put the power. This would also mean I'd have 1 to the negative first power and 2 to the negative first power. Well, 1 to any power is going to be 1. But then if I have the 2 to the negative first power, that means I'm going to actually bring it to the top, and I'm going to bring it from the denominator to the numerator, and that's going to equal 2 to the first. And as I keep writing a negative, Lordy B, I'm having a struggle there. So it's going to be 2 to the positive first power, or just 2. So when x is equal to -1, y is going to be 2. And so it's going to increase as x goes down, goes to -2, it's going to be then 4. As x goes to +2, it's going to be 1/4. And so that's why it's just going to be that opposite. And so it's this function. Okay. Now, if it happened to be negative, then it actually pulls it down to the other side. It'll be on this side of the graph. But we're going to actually focus on just those two right now and the transformations of those. So when I have, when I have 2 to the x plus 2 power, remember this is within my function. And so way back when we did parabolas and we had like y equals, and we had, let's say, 2 times x minus 2 expression squared plus 1. Then this was a parabola, and I knew that since it was inside my function, that it was going to move. Do you remember which direction? This one tells me I'm going to move left or right. When it's going to be then minus 2, remember you're going to go to the right. And so like an x minus c, and so it's going to look like this opposite. To me, it looks like a -2, which means you think left, but it's really the opposite, so it is going to be, in this case, it's going to be right. But then the one that's on the outside is going to be when I move it up or down. And if it's going to be plus 1, you keep it the same. So in this case, on my example, it's going to be up. Well, I did the opposite for this function here. So I know that my parent function for 2 to the x plus 2 minus 1 is going to be the f of x. Let's just maybe go p of x as a parent function of 2 to the x. And so it looks like it's going to look very similar to this. I'm just going to go dashed right now because I'm going to move that because it's going to have a shift. But inside, since I have an x plus 2, and it's in my function, this is going to tell me left or right. When it's going to be a plus 2, that would indicate that I'm going to go then to the left. It's going to be the opposite. Okay, if I had a minus number, say I'd have a minus 5, that would mean I would go right 5. But in this case, my example is just going to be to the left 2. So every point that I had earlier, when x is equal to 0, y was 1. When x is equal to negative 1, it was would be 1/2. Then what happens is all of those are going to shift to the left. So I'm going to come over to the left 2. But then this is the number on the outside. This is going to tell me up or down. Now because it's a minus 1, that means I'm going to go 1. So on this point right here that starts off with 0, 1, I'm going to move to the left 2, but then I'm going to come down 1. Now, when I had my horizontal asymptote, I'll just go ahead and put it in red. I have earlier I had a horizontal asymptote at my x-axis, and since I'm shifting everything down 1, now my horizontal asymptote is just going to be then at my equation y equals negative 1. It's also going to be the same thing as what you're adding or subtracting. Then this point then is going to be the one that comes close. It's going to cross here, but then all of my other points, when x was equal to 1, y was equal to 2. That means that's going to come over 1, 2, and then down 1. And so that will be my new point. So I'm really looking for, can you describe it? Can you tell me that it's going to go left 2 and then down 1? That's going to be a pretty big part of my function. Now let's go ahead and talk about then the domain and the range. So when I had my parent function up here, okay, this is going to be like I had before. My domain is going to be then all real numbers. So it's going to be from negative infinity to infinity. My range, remember, I'm never going to hit the value of 0. So my range is going to be 0 to infinity, but because it cannot equal 0, it's going to have a parentheses on both sides. So then when I shift it, my domain and range also have to be well, not really, I guess my domain. My domain stays the same, right? My domain is going to be, my domain is going to be negative infinity to infinity because x can be anything, but my range, that one does switch. So in other words, my lowest value now is going to be negative 1. Okay. So then I'm going to make sure I put a parentheses on that because it will never hit negative 1. Oops, sorry. All right. Now we're going to also talk about the letter E, and E is going to be our natural log, okay? And it's from Euler's number, and Euler's number is defined as this formula, 1 plus 1 over n all to the n power. And what happens is it's going to be it's an irrational number, meaning it's a non-ending decimal, and it never repeats. So remember, we had the value pi is also a real popular irrational number, and you know that the pi starts off with 3.14, but it continues on and on and on. Well, E is kind of the same thing, and it's, make it approximate because it's never going to equal that, but it's about 2.7. And most of your calculators should have the value of E in your function, on it as well. So if I look at E, my calculator shows it right here with the ln(x). It's always going to be associated with what they call the natural log. So they're going to put the natural log as your main function, and then e to the x. So my calculator, I can go e, and if I just tell it to the first power, then it gives me that value of 2.71 8 to 8, but it continues on and on and on forever. Okay? So, and E, we actually use in a lot of different things when it comes to like exponential growth and decay. We'll also use that. So when I have the value of E, so I'm going to go ahead and go my X and my Y value, just like we did before. When I have 0, in this case, if I have E to the 0, I'm going to go minus 1 plus 2. Let me just start with my parent function. I'm going to go over here. I'm going to go f of x is equal to e to the x. Let me ask you, have you dealt with e? Do you remember dealing with e last, like in Algebra 2?
Not really,
Maybe a
no.
little. Okay, let's start with just the parent function. Okay, so I'm going to graph that one, and then I'm going to work on my shift. So I'm going to go my x and my y, and so if I have e to the x, I'm going to start off with 0 again. I'm going to have e to the 0 power. Now, anything to the 0 power is still going to be 1, and so that's where I have that value here. When I have then, when x is equal to 1, I have e to the first power, and that's going to be approximately 2.72. Okay, so I'm going to come over when x is equal to 1, y is going to be 1, 2, and just almost 3, but not quite there. Okay, when x is equal to a -1, then I end up having then, if you want to, you can also use your calculator to get an idea. But if I put that in, then I'm going to get it's 1 over 2.7, which would be about 0.3678. 0.367, let's go 9. Okay, so in other words, it still has that same shape that we had earlier, and it's going to look a lot. I'm just going to go dashed right here because I'm going to my function that I'm asked to graph actually has a shift in it. Okay, so I'm going to start off with this one. I'm just to get an idea. Inside, it's going to be x minus 1. So that's going to tell me I'm going to either go left or right. 1. Can you tell me? Right. Very good. So I'm going to go right. 1. But then the 2 tells me I'm either going to go up or down. So am I going to go up or down with a plus 2? So I'm going to go up 2. So this same function now, and I'll get a different color, is going to go from 0, 1 to now I'm going to go right 1 and then go up 2. So then when I have this function, I'm going to still go almost 3, so I'm going to come over 1 and I'm going to come up 1, 2, 3 and be a little shy. And then my graph, my horizontal asymptote is going to be at what point? If I'm going to go up 2, it's now going to change to y equals 2. And so my graph then will look a little bit like this. And if you get stuck, put some numbers back into the equation. So again, I go x to the e minus 1, and then I'm going to go plus 2. So in this case, this one, you could still go second e, and then to the -1 power. And then you're going to go then move over and then plus 2, and that will give you a value of the 2.36. So in other words, this point here had to move over 1 and up to 2.36. So again, what I'm looking for when you're testing, and probably on your homework a lot, is what's happening with your original function. Is it how is it moving? Now, compound interest also uses a couple of different ways to, and interest is actually something in the bank. You call that the principal, and we talked about that in modern college math. So the principal is what you put in, and then the interest is going to be then you are accumulating interest from. And there are two main formulas. So if I'm going to compound interest, and it's going to be so many times a year, that I'm going to use this formula. If I'm going to continually compound, then I have a new formula, and it's using that value of e. So it's e to the RT power. So the principal times e to the RT. So in this one, boy, I should have probably put it on a new page. This is going to be, we're going to do skinny. So A is going to be compounded semi-annually. So what I want to do is I want to first find out what my P, my R, and my n and my t is going to equal. And then what will happen then, as I'm compounding at a different rate, that's the only thing that's going to change is going to be my n until I get to compounded continually, and then I'll only use the p, the r, and the t. So in this case, if I find the cumulative value of investment of $5,000 for 10 years, that is an interest rate of 1.56%. If the money is A, compounded semi-annually. So P is going to be 5,000. Okay, R is going to be, yes, but I want you to remember we have to move that into a decimal. Because it's a percent, you need to make sure you move the decimal over 2 places, so it's going to be 0.0156. So I'm going to put my rate as 0.0156 as well. Now, n, if it's semi-annually, that's how many times it's compounded a year. So semi-annually would indicate that it's going to be 2. And then my time is going to be the amount of time that I put that in. So in this case, it's going to be 10 years. So then I'll go ahead and I'll put it back to my formula. My formula is going to equal, I'm going to have 5,000 times, and then 1 plus my rate, which is 0.0156, divided by n, which is going to be 2, all to the 2 times 10 power. And then I'll put it into my calculator. And I know a lot of times you guys go straight across. I sometimes will just like to do my parentheses. I start with this one, and then I add one, and that helps me so I don't. If I don't get a parentheses quite right, then it will mess things up. So I'm going to take my rate divided by 2. I'm going to add 1, and then I'm going to take it to the 2 times 10 power. So I'm just going to do that. My head is 20. And so this amount right here is going to be then the 1.68. But now I have to take it times my principal. And so my final answer is 5,840.59. Oops, I'm getting it a little bit. Then I'm going to continue on, and all I'm going to change on B is that I'm going to change it quarterly. So everything is going to stay the same, but this time n is going to equal 4 because I'm going to do it 4 times or quarterly. So I'm going to start off, I'm going to still have A equals 5 times, I'm going to go 1 plus 0.0156 divided by now 4, and then it's going to be 4 times 10 power, to the 4 times 10 power. So then I'll go 0.0156, I didn't get the 1, 0.0156 divided by 4 plus 1 all to the 40th power, and then I'll take it then times my principal. Now, for your test and down the road, I would like to see this formula because so many times I get the right formula, but there might be a difference in the answer just because of the way we hit the button wrong. So it's going to be 670.28. Fact, something, did you get the same thing? I'm going to try that one more time. This should actually increase just a little bit. So something went awry. So 0.0156 divided by 4 equals plus 1 equals to the 40th power, and then times 5. 1, 2, 3. I did do something wrong on the first one. So just to know, what's going to happen is each of these are going to get just slightly above. So if you get something that doesn't jive that way, that kind of gives you a clue on whether you. So now I have 5,842.35. Make sure it's a money. And C, I'm going to end up doing the same thing, but this time it's going to be quartered monthly. So N is going to change now to 12. So I have still A is going to equal 5,000, and that's going to be 1 plus 0.0156 divided by 12, but to the 12 times 10 power. So while we're doing this, when I'm plugging this in, Why is that not changing that much? Can you think about the reason why we're not seeing a huge difference in this amount? Okay, interest rate's small, but really the fact rate that this is always going to be about about 1. I mean, and so when I take 1 to any power, I'm always going to get something about close to 1, and so that's why there's very little variance or change in it. So let me see, I'll go divided by 12 plus 1, so I get it close to 1. I'm going to now take it to the 120th power, which seems like it should be a big number, but remember it's still going to be just about 1. Whoa, times 5,000? Did we not move enough?
No, not.
So I have then 5,843.54, and we need to move so that we have, like, I hate it when that does that. And notice that, again, I'm just then a little bit more than what I was on each one of them. My last one is compounded continually, and I'm going to put it on the back. But I'm going to use this formula of A equals PE to the RT power. So on the last one, D, A is going to equal, or D, PE to the RT power. And again, my principal, my rate, and my time stay the same. So I'm going to start off with my principal, which is 5,000. I'm going to take E to my rate, which was, remember, the 0.0156. But then I'm going to take it times then my time of 10, not T. My time is going to be 10. So in this case, I'm going to start off. I always like to start with E. So I go E to the, and then I go, since it's 10, okay, I'm going to go ahead and just go, I can actually go 0.0156. Sometimes it's not 10, but you should be able to stay within your exponent and multiply it times 10. I know I could do that one in my head, but that's enough way to do it. Out of that top part, I go equals, and then I have to multiply it times then my 5,000. And so this time, I end up getting 5,844.13. Now, notice again, if I have 5,844, comparing it to my other ones, it's only about, for my very first one, $4 difference. So sometimes they'll use that compounded continually as kind of a selling point, but in reality, it's not much, because that's over 10 years. So imagine $4 over 10 years. Not a whole lot of difference there. Okay.